Sure. So just before we get started, I did want to let everybody know that this is a research submission, and so I'll be using the entire 5 minutes just for the presentation. And the code and the paper for this project are both in my submission file, and I can provide them to you after this if you'd like. So let's get to it. Hey everyone, my name is Aditya, and I'm a 16-year-old looking to leverage deep learning to solve real-world problems. Over the last couple of months, I've been focusing on the optimization landscapes of neural networks, what these landscapes can tell us about model performance and generalizability, and in particular, how we can use these landscapes to skyrocket something called knowledge distillation by targeting saddle points. Models today have three key problems. They cannot run locally on small devices due to their size, are extremely computationally expensive during inference time, and have a sharp performance size trade-off. Real-world problems are very complicated, and if we want to solve these problems, we need models large enough to represent potential solutions. But the larger we make these models, the more expensive they become computationally. We have a trade-off between performance and impact. And this is one of the most critical problems the industry is facing today. Building a 10 gigabyte model with 500 million parameters that detects malaria in blood smears with 99% accuracy doesn't matter. We can't fit a model of that size onto the medical equipment and lower end computers of local hospitals and communities. Irrespective of accuracy, we can't fit large, high-performance models on traffic lights for accident detection, on ECG devices for cardiac disease discovery, or on smartphones and wearables to predict health metrics. The size of our present-day models is significantly decreasing AI's potential for impact in the 21st century. This is the problem that knowledge distillation, our current solution, aims to solve, but unfortunately, it just doesn't work well. KD has a simple idea. We have a large teacher network and a small student network. And rather than the student optimizing a loss function like cross entropy, the student minimizes LKD, which is typically the difference between the student and teacher's output logics. The hope is that the student learns to mimic the teacher over time and hopefully becomes even more accurate than the teacher. In practice, however, this simply does not happen. KD empirically results in poor students with minimal generalization increases. Research has shown that it actively hinders student convergence after initial descent, and rather than actually distilling valuable information to students, merely acts as a form of regularization that smoothens the teacher's output labels. With current methods, teacher models are actively preventing students from finding better, higher order solutions. So how do we solve this, make KD more effective, and unlock AI's potential for impact? The answer lies in the lost landscape. In the self-distillation case, every teacher is a little packet of information about the optimization landscape of that problem. More specifically, all the saddle points encountered by the teachers serve as landmarks that signal further potential for descent in that area. In high-dimensional problems, which is what neural nets deal with, saddle points are infinitely more likely to occur than minima or maxima. And today's KD algorithms are unfortunately slowed and trapped by these points due to their high error regions. However, these saddle points also have substantial directions of negative descent. So if we can avoid their high error regions, we can force our students to re-explore those regions by biasing the student in directions with the largest negative eigenvalues, using these saddle points to our students' advantage. And that is the foundation of our new technique, saddle point reversion for knowledge distillation, or Sprkd for short. For every teacher that we train, we repeatedly compute the determinant of the Hessian matrix to check for saddle points. If the teacher is at a saddle point, we store it, building a huge repository of areas of the lost landscape that show high promise for re-exploration. We then average the highest performing saddle points to approximate the region of highest potential improvement and initialize our student to this calculated region. Over time, we decay the influence of the teacher saddle points, eventually removing all teacher interference. The impacts: we drastically reduce training time by eliminating initial descent, allow the student to develop higher order relationships by building on the optimization of teachers, and allow the student to independently discover better solutions while still using the teacher as a guiding compass. And empirically, this method yields great results. On CFAR 100, our ensemble of 3 teachers had 88% accuracy after 100 epochs. But with Sprkd, our student attained 96% accuracy in just 10 epochs, 8% more accuracy in just 10% the training time of traditional approaches. Sprkd drastically increases performance while decreasing model complexity, and ultimately opens the door for AI to truly impact those who need it most. Thank you.
Thank you for your presentation. Judges, do we have any question for him?
So this is really interesting work, and I'd like to dive into it a little bit more deeply. So in one of your slides, you talked about averaging the teacher parameters and using that to set the student parameters. But how do you map teacher parameters to student parameters if these are networks of different sizes?
Yeah, I'm actually really glad you asked that question. And that was actually the central focus of our research for like the last 2 to 3 weeks that we've been trying to fix. So basically, we first focused on the self-distillation case, just to see if this concept worked, and then we moved on to knowledge distillation. Now, in the self-distillation case, what we simply found is just analyzing the eigenvectors and eigenvalues will give us the respective saddle points. Now, of course, what we want to do is arrive at distillation techniques, right? We want to make our models smaller. So what we decided to do is create a almost 3-phase knowledge distillation system. So you would have your teacher A, which would distill itself into teacher A prime. And then we would use traditional knowledge distillation to distill the improved teacher down to the student. So what happens is that we use the traditional knowledge distillation approach to essentially, well, distill our improved teacher, but we make the teacher so much more effective and impactful that it improves the results of traditional knowledge distillation approaches.
Okay. Let me ask about this saddle point idea. So you're defining a saddle point as a point where the gradient in some direction, or actually the Hessian, in some direction is 0, right? In other directions, it's not 0, or it's in opposite signs, right? So in some directions, it's positive, in other directions, it's negative. But are these stable states of the network, or are they just states that it goes through temporarily? So, it's not trapped at a saddle point, right?
Yeah. So basically, there is a really interesting paper that answers the question you were mentioning. You might have read it, where it basically mentions about how saddle points kind of proliferate as dimensions explode. So what we found through our empirical testing is that despite the fact that neural networks don't get stuck in saddle points, our teacher neural networks a lot of times crossed these same saddle points. And we found that we could use them as almost markers of sorts that said, hey, the teacher has passed this particular point. There could be areas of further descent here, but the teacher chose to go down path A instead of path B, for instance. And as a result, when we not really trapped, but when we stored those saddle points and gave them to our self-distilled students, the students were able to use those saddle points and actively target their negative direction. So more specifically, what we did, we took the eigenvectors of the largest negative eigenvalue of the Hessian matrix, and we multiplied the current model's parameters with those. And as a result, the students were able to actively target those negative eigenvalue directions and rapidly descend faster, which is actually what led to the 8% more accuracy in like drastically reducing training time at the same time. So
I guess I don't understand why this leads to improvement. I mean, if you're just calculating the gradient and descending, along the steepest gradient, why is, you talk about alternative paths from the saddle point, but what's going on there? Where is the optimization different than just doing gradient descent?
So the key difference here, I guess I can just reiterate on this. I think I should probably just explain the algorithm, what exactly we're doing. Basically, what we do is store not just, we basically just store the saddle points of a given teacher, right? Rather than storing different pieces of the optimization landscape. And rather than just doing gradient descent, what we do is initialize the student to that averaged area where saddle points are the most likely to occur. So that difference in initialization combined with using the second order method, as opposed to a traditional gradient descent, which is a first order method primarily, those two things combined are what's fueling and is the backbone behind most of our improvements.
I see. And what's the second order method that you're using?
So as I mentioned before, we use the Lanczos iterative method to approximate the eigenvalues of the Hessian matrix. And using this approximation, we not only determine saddle points, but we can use their respective eigenvectors to take a step in the direction of the greatest, in the step of the greatest negative eigenvalue of the Hessian matrix. So that's where the second order method comes into play, as opposed to just stochastic gradient descent.
Got it. Thank you.
Yeah. And I can actually send you the paper with the full algorithm if you'd like to see that as well. So yeah.
I think it's in that Google Drive folder,
Yep.
right?
Sorry to jump in, but we're running out of the time.
Okay, where are you located? What school are you in right now?
I'm at the Woodland Secondary School, enhanced program, currently grade 11.
And where is that located?
Ontario, Canada. So
Ontario, Canada. Okay. Thank you.
Thank you.
Very impressive work.
thank you, appreciate it.
Thank you for joining us. So you can leave the judging room right now. Thank you.
Absolutely. Thank you so much for your time. Appreciate it.
Thank you.